specialized in steam turbines, gas compressors, gearboxes, couplings, machinery in general, actually, motors also, gas turbines off and on. And I have been doing roughly about 32 years of rotating equipment experience with reliability analysis, vibration analysis, you can say failure analysis also, root cause failure analysis, for many kinds and sizes of machinery. So these are the original steam turbine power generation units. As an example of one from 1941, it's constructed by Brown Boveri of Switzerland, who later became ASEA Brown Boveri, which is ABB. And later it was purchased by Alstom, which was now purchased by GE, it looks like. I think this division itself is still now probably owned by GE. But from Brown Boveri to ABB to Alstom and forward. So I brought up this picture to show an example of how steam turbine and gas turbines, of course, are related to heat. They require heat to operate. You can't run them with cold steam or cold water. They need, well, hydro turbines you can with cold water, but steam turbines require hot steam. So high temperatures introduce thermal problems. They introduce thermal transient expansions in the casings, thermal transient expansions in the piping, thermal transient expansions in the rotor itself. And this is a 51,000 kilowatt turbine train. So on the left-hand side, you see the high pressure turbine. And on the very left, you see the governor valves. And on the right, it looks like these are the stop valve controllers. These are on the two valves there on the right. These would be separate stop valves, either for reheat or just purely inlet. And then you have the IP with the large pipes coming off the top, IP section, and then the LP. And finally, toward the end is the generator. So these machinery from the beginning started experiencing vibrations. Here we have a cross section of from 1931 of a 36,000 kilowatt, 3,000 RPM STG unit, also produced by Brown Boveri. They obviously rely on steam at the inlet. Here we have the high pressure steam on the inlet side. Let's see if I can get this mouse going. There we have high pressure, intermediate steam pressure here, and we have an LP turbine at the end. These steam turbines are, I'm just admitting some students here. Okay. These steam turbines have always exhibited sensitivity to vibration, even from the beginning. Dr. Charles Parson experienced vibration from the beginning. Why? Because the steam turbines have rotors and operate in a high speed, rotational speed, whereas the older technologies was reciprocating engines, steam engines, and these had no rotodynamic issues. So rotodynamic problems really only came up with steam turbines because they're the first to reach high speeds compared to what man normally manufactured in the 19th century or the late 18th century and the early 19th century. So with the higher speeds, they got into problems of whirling, bearing, unusual bearing vibrations, high temperature reaction of the rotors would cause unbalances, and many unusual problems. So if you go back to the history of the Parsons turbines and Westinghouse licensed Parsons turbines in New York or in other power stations, they had many troubles trying to solve the vibrations. Why is that? Because the science of vibration analysis was not clear at that time. It was black magic, or gray magic, we can say at that time. It's quite unclear to everybody. And there was no advanced instrumentation at the time. In fact, there's hardly any instrumentation at that time. So you can see they're trying to deal with it by guessing and by opening the machine when it has a high vibration, finding out what was causing the vibration, because you cannot know when it's operating outside as it's operating externally. There's no instrumentation to follow up on why it's vibrating. So, oh, hang on, we have a few more students, it looks like. Okay. So we can go on to the next slide. This is just a nice cross section showing the technologies from the old days. Okay, and PowerPoint doesn't want to react immediately. And there must be a slowdown between PowerPoint and Zoom. So it'll just take a few seconds. So as long as we're on this slide, we'll just continue talking about it. As you can see, as high temperatures enter through the casing, through the steam entering in the casing, there will be deflections in the casings. They will not grow exactly perfectly well thermally. And the same with the rotor. It doesn't grow perfectly, especially at startup conditions, and even when it's warmed up, because there's a hot steam entering, and this is going to impact with a higher temperature in some parts of the rotor, but at other parts of the rotor you have lower temperatures. Now we don't need exact uniform temperature from left to right on the turbine, but we do of course need a uniform temperature at each section to minimize a thermal induced vibration. So I'm having an issue here with switching on the slides. Gentlemen, if you can give me a few seconds, I have to.
Yeah, take your time. Take your time, no problem. Take your whole time. No rush. Yeah, if you want to close the PowerPoint, open it again, take your time, no rush at all.
PowerPoint won't even close right now. Okay, there we go. Okay, I have no idea why it's stuck with. Okay, can you hear me, Mr.
Yes,
Salah?
can you hear it very well? We can see the presentation, and yeah, sometimes this has happened for no reason. So yeah, don't worry about it. So yeah, please.
Okay, very good. Okay,
thank you so much.
Thank you. So we have a here's a modern steam turbine, 360,000 kilowatt this time instead of 36,000 kilowatt. This one is 360,000 kilowatt, year 2000. And on the left we have a HP turbine. On the right we have a an IP turbine casing. And as you can see, the general steam technology has not changed much. You have rotors, you have blades on them, you have a coupling, you're going to have different casings. Each casing is bolted, each rotor is bolted to the next. Nowadays in modern turbines, obviously, anytime you're above something like 760 or 70 megawatt, the couplings will be solid and no more flexible. Solid hubs, solid coupling hubs. However, the problems of the past, which was heat-induced problems of vibration, heat-induced rubbing problems, rotodynamic problems, manufacturing deficiencies, they haven't changed. So we've been now in steam turbines for 120 years at least now, and the same evils are still hurting a modern steam turbine. However, bearings are much improved, thank God. That helps a lot in providing damping to those vibrations. Balancing of rotors is far improved from the old days. So we have modern tools that help us. Number 3 modern tool is vibration analysis, high-tech instruments and high-tech vibration analysis. Knowledge is amazing. So we'll go on to the next slide. Okay, we have one student entering. Now, we have, on this slide, we discuss thermal transient vibrations and where they came from. So thermal transient vibrations are related to unequal rotor temperatures in turbomachinery, leading to unbalance. They introduce a 1x, a 1 times running speed, unbalanced vector at rotating frequency, and occur in power generation units mostly. This includes steam turbine rotors, gas turbine rotors, generator rotors. Other than the rotors, we have non-rotor sources, which include thermal growth at bearing housings and supports, or piping vibration expansion strains. These thermal transients impact field balancing, data gathering. So the thermal transient vibrations, as we said, are usually mostly related to rotors. However, they can also be, of course, caused by bearing housing support growth or piping temperature expansion and strains. And when we're going to do field balancing to reduce such unbalanced vibration, it must be done carefully. You cannot use unsteady data of amplitude and phase. So you typically wait until steady phase and amplitude is reached at the balancing runs, which can take hours. So depending on the size, I mean, on a 20 megawatt steam turbine driven generator, the time to stabilize thermally on a new machine and in good condition, it could be after a long preheating period, could be 2.5 hours. But if you come to a one in not very good condition, worn out and has internal problems, then it could easily be 4 hours. And that's only on a 20 megawatt. So this means if we come to a 75 megawatt machine, you're going to be looking more at, depending again on how well it's designed and how well it is maintained. It could be 4 hours, 6 hours, 3 hours, depending on load and design, quality of the bearings also, design of the bearings. It's recommended to take no load at first, and then partial load, such as half load, and then full load run data to compare and improve balancing. So this is especially regarding the which is the generator itself. The generator is more sensitive to running at half load and full load, because if it's a 100 megawatt generator, half load is only 50 megawatts and full load is 100 megawatts. That's a lot of difference in thermal heating. That generator runs at 100 megawatt with a lot more electrical load entering through the stator windings and through the rotor. And this greatly increases temperatures. So therefore, as you can see, for especially generators, you definitely want to run as close as you can to full load running. However, it's good to also take no load, because you want to compare why at a constant speed, you're trying to compare the no load, for example, 3,600 RPM is the synchronous speed, 60 hertz, for example. You want to take the no load to see what is the normal unbalanced vector on the rotor. And then when you go to the full load, you want to see what's the thermal unbalanced vector, which is additive to the normal balance vector. We'll just add some more. Oh, okay. So in more detail, transient thermal vibration sources include thermal bowing of rotors, labyrinth rubbing on the rotors, electrothermal heating hotspots at generators, thermal inertia of turbine rotors or generator parts, non-homogeneous forged rotors. Rotors which have a non-homogeneous forging will deflect thermally, and they will not straighten out. Also, loosening of built-up turbine wheels. Built-up turbine wheels means where you have a shaft and the wheel is slid on with hopefully a shrink fit and typically a keyed connection. So it's not an integral rotor. And if these loosen, then they cause unusual vibrations, which will end up having a thermal component. And then you have misalignment on coupled machinery trains. This introduces thermal transient vibration also. Overall, it can be confusing to resolve because correct phase angles and amplitudes are distorted by nonlinearity. So, before balancing, must first resolve nonlinearities such as misalignment at bearing housings, misalignment at couplings, looseness in foundations, looseness at bearings, and looseness at bearing housings and piping strains. If this is not done, you're going to end up with poor balancing. So this final recommendation here is not to apply balancing or trying to search for the thermal transients or do a final balancing of thermal plus mechanical normal unbalance, residual unbalance, by simply attaching weights. No, what you first want to do is ensure there's no nonlinearity in the system by searching for misalignment at the bearing housings themselves, between bearing and shaft. Next, misalignment at the couplings, looseness in the foundations, the bolting, the concrete cracking, looseness at the bearings, meaning excessive clearance between shaft and bearing, and piping strains. These all introduce stresses and forces that will twist the casing, twist the shaft, and cause vibration that is additive to the thermal transient vibration. And in fact, some of them are thermal transients themselves. Okay, let's hope it works now. It's sticking a little bit again. Again, we'll just need a few seconds to get this.
No problem. Take your time. That's fine. Thank you.
I think we need to solve the problem between PowerPoint and Zoom.
That's okay. Take your time.
Okay. Okay, I think what has to be done is you have to left click on the screen with your mouse, and then it will allow you to go forward. Yeah. Okay, so up to the next slide. Modern thermal power plants are still experiencing troubles with thermal transient vibrations and thermal transient stresses. Obviously, thermal transient stresses caused by unequal temperatures will also cause thermal transient vibration because the mass has changed with regard to the center of geometry of the rotor due to thermal transients. So this is a high pressure steam turbine, HP, casing, and rotor. Rotor will have different sectional temperature distribution, leading to unequal thermal growth. So as you can see here on the right hand, you have the red color, the hottest section. We have the blue and the large mass of the main inlet turbine wheel. So the main inlet turbine wheel is having actually a colder temperature in the center because why? To the left are lighter section parts of the rotor, and they will heat up faster. But this is a heavier section, so it takes more time to heat up. Anytime you see the higher differential temperatures, it means there's thermal stresses, but also unequal thermal growth. Leads to thermal bowing and unequal radial growth. Result is rotor vibration at 1 times running frequency. However, if it's excessive, if the bow is excessive, you're going to get a rub at the labyrinths. And there you're going to see a 0.5x vibration, or it could be a 0.49x vibration with backward whirl. A rub will never cause forward whirl. A forward whirl would be caused by an aerodynamic excitation, such as if you had a steam turbine and it has a steam whirl. In that case, there will be a whirl caused by the steam leaking in the seal areas and at various places, or at the outer diameter of the tips of the blades. Anyway, the steam whirl will cause a forward whirl, while a rub caused by any rub will end up causing a backward whirl. Because why? As the rotor was rotating in one direction and a rub occurred, the rub causes it to slow down momentarily because it's acting like a brake. It's a metal to metal rub. So it's the rotor rubbing, for example, against the stator. And it causes a momentarily backward, just obviously it's going to keep going, but it sees it as a momentary backward rotation compared to what the normal rotation it was doing in the forward direction. One final point here is some forgings are heat sensitive. This means that even if allowed to heat up slowly and evenly, it will still deflect somewhat. There's limits to this deflection. In fact, there's in the API and international standards, there are limits to what a forging is allowed to deflect when it's manufactured and final machined at the factory. This is in the API, for example, 612 and in other standards. So we'll go to the next slide, I hope. Okay. So what's the different, we go back to the different sources that we discussed. Now we look at one source, rubs. Okay. Rubbing is causes a hot spot due to friction. So we have here, here's our rotor, and we have originally it came with a residual unbalance, which was not severe. It might have been, for example, causing only 1 mils vibration only at 3,000 RPM. Let's assume it's a 50 hertz generator or 50 hertz steam turbine rotor, and it's operating with 1 mil 25 micron vibration, 25.4 micron vibration. Now, during startup or during operation, the machine had a rub with the labyrinth or somewhere in the casing. So the result, oops, where is my mouse? Okay, there we go, sorry. So if we had a rub at this local hotspot, it would end up causing a thermal growth of the shaft at that hotspot, which is exemplified by the pink dot. So we have a thermal unbalance vector that's purely just thermal unbalance, whereas we still have our residual unbalance here. Okay, so then we have a resulting final vector, and of course, the original unbalance had a phase angle that was in this direction over here. This was the phase angle before, and the new thermal unbalance had a new different phase angle over here. And the resulting unbalance is going to be a combination of the two phase angles, of the two unbalances as magnitudes and phases. Okay, so if you were going to do balancing, you're going to find difficulty here because this thermal unbalance can come and go. The magnitude of this pink dot can grow upward, or it can go downward depending on how much heating was occurring. So then the question is, where do you want to balance it? And do you want to balance it? In other words, wouldn't it be better to somehow first solve the rubbing and then you can get rid of the thermal unbalance that caused this and this example? So this is a question that the vibration analyzer should ask himself. Do I immediately just go and try to balance when I see thermal imbalances? Or should I do some minimal corrective action to resolve the vibration by other means? In other words, solve the root cause, which would be a local rubbing. Okay. However, in other cases, you might have no time to do that. And therefore, it would be better to just do a balancing. However, as we mentioned, it has to be taking into account other factors, which we mentioned here, is phase angles and amplitudes can be distorted by nonlinearities. So check for misalignments at bearing housings, misalignment at couplings, loosens in foundations, and these other issues. Don't just jump on the machine and throw weights. It's not the right solution. Here we have a next example, a nuclear steam turbine generation unit. It's the generator itself. They suspected it has a seal rub because they were getting a variation in vibration on the bearings. As you can see, the amplitude, how it varies. The smoothest is something like almost maybe 5 micron, and it's going up to a max of around 50 micron. So really going from 5 micron up to 50 micron, which is something like 2 mils, almost 40 micron, which is 1 mil and 3/4 approximately, in a period of 12 hours. So why would it have a period of 12 hours? Okay, we'll go back to this. So we'll read what's on the right, on the left hand, the comments from the person who had this problem. So thermal rub stress, well, this is, well, I've added this. Thermal rub stresses can produce cyclic vibrations which occur transiently in steam and gas turbine rotors or generators. Now, from the author of that paper, he mentioned there's a change of the 1x vibrations versus time at transducer location B20 generator, on the generator, and on the exciter side. The amplitudes are changing between 10 to 50 microns. The period of one cycle is about 12 hours. In gas-cooled turbo generators, shaft sealing rings are fitted to prevent the hydrogen gas in the stator space from leaking past the shaft into the surroundings. So you have to seal it inside. We don't want to lose the hydrogen, and it'll also cause a fire. So in this, the seal uses oil lubricated components, and that's to stop friction that might cause a sudden spark or rubbing. And however, there can be sometimes a contact between the rotating ring and a stationary ring. And then heat arises from the resulting contact, and friction losses occur, and the friction losses are transferred into the shaft as a rub. So basically, they considered the cause was a rub by the shaft seals, and then it would go up and down. Now, if we ask why a periodic cycle of 12 hours, it means there must be something else involved. So they didn't mention this, but to get a cycle of 12 hours means that, number one, it could be due to night and day thermal growth of the foundations of the machine. Okay, they would push up the generator bearings up or down slightly and cause a change in the alignment of the seal to the shaft. And that small change could cause the rubbing. So that's why we see a change from every 12 hours, which would be night and day. That's one possibility, and it's probably the most likely possibility. The other possibility is that if their lube oil temperatures are varying from day to night significantly due to the cooling water, for example, then it could be that the change in oil temperature, meaning viscosity, is also feeding this variation in amplitude. Okay, and that would be in the bearings themselves, the generator bearings. Okay. Another example, here we have a gas and steam turbine on one train, 350 megawatt output. It's a cogeneration unit. And this is the time versus vibration amplitude on the main bearings of the machine. And trended with power, with megawatt. The blue on the top is the megawatt power. And the other MVR is the magnetic reactive power. So we just stick to the active power, which is the megawatt. So you can see at the top, they're almost reaching rated power of 330 megawatt. And as they started from 0 time, we have the vibrations coming up, okay, gradually. And once it's reached rated speed, you can see the rated speed basically by the right here, okay? So from here on, we're seeing variations in the vibration at each bearing. The bearings are, the red color is the compressor bearing X probe. So it'd be the gas turbine compressor bearing. And the blue would be compressor bearing Y probe. So that blue there is compressor bearing Y probe. Then we have the IP turbine bearing X probe, purple, over here. And we have the IP turbine bearing Y probe, which is highest value here. Okay. Then we have HP turbine. Oh, we have some more people entering. Okay.
Sorry, Engineer Abdulrahman, just by the way, for yourself and all the participants, I'm very sorry for this admission thing, and I know it's disturbing, but I found a solution for it. We'll do it from the next session. It will be auto admission, so it will not disturb the presenter anymore. Thank you.
Great. Thank you. Great. I just admitted some more just now. Okay.
Thank you so much.
Okay. Yes. Looks like we'll be going a bit over time because we had some delays at first. So you can give me a few minutes of.
No, take your whole time. You the last one, and actually the presentation is amazing. So
okay, great.
Take your time. No problem. Thank you.
Thank you. Okay. And as we said, the tan or brown color, if I can bring my mouse here, is showing the highest, and that would be the IP turbine bearing Y probe. Then we have an HP turbine with basically a black color, HP turbine X probe, and we have an HP turbine bearing Y probe, which would be the green. Okay, so what was occurring here, as you can see with time, so this is minutes, 3,500 minutes is the end of the scale. We start out as 0. So 10 hours would be 600 minutes. So this would be right here where my mouse is. I don't know, Salah, is my mouse clear?
Yes, I can see your mouse very clear.
Okay, very good. Okay, so this would be 600 minutes would be 10 hours. So this is 10 hours. And if we went to, where'd the mouse go? There we go. If we went to double that, it would be 1,200 minutes. So this would be 20 hours, okay? So 24 hours would be roughly here somewhere. Roughly here would be 24 hours. So as you can see, there's quite a bit of variation in 24 hours. If they had finally got it started up after roughly 10 hours, in another 12 hours roughly, or 14 hours, there's quite a bit of variation. Here's the variation here, for example. We have the turbine, IP turbine Y probe is dropping down to roughly 110, and then shooting slightly or gradually growing up to 210 microns. So that's a lot of microns, basically 110 to 210. That's about 4 mils. So 4 by 25 is 100 mils. So about 4 mils vibration variation. However, gradually it starts to settle down and it's becoming smoother here. Not the best, but smoother. In proportion to the size of this machine, if we say 350 megawatt, it's not acceptable. If you look at the rotor vibration at this, the IP, we're talking a continuous operation at 175 micron. It's too high. Typically, the max allowed to be considered smooth would be 100 at this size machine, 100 micron max, if you want to consider acceptable. So they're quite above. So is there a problem? The answer is yes. What's the solution? Trends like this are great, a very important studying tool. The other is actually the orbits at each bearing, vibrational XY orbits at each bearing. Even casing vibration is good to have. Casing vibration in a vertical and horizontal and axial direction are very helpful to judging. Why? The casing vibration is great for judging the amount of axial misalignment occurring, because you end up with having a high axial vibration on the casings when you have the misalignment. And it's a very good indicator. So the axial vibration should never exceed 50% of the radial vibration measured using seismic probes on the bearing housings. If it's exceeding 50%, you definitely have an axial vibration that's typically caused by misalignment, although it could also be resonances somewhere in the supports. So rarely it can be resonances in the supports, but typically it's due to misalignment. So why do I talk about misalignment here? Because they found the problem was it was both a thermal transient vibration occurring and it was a misalignment at the bearings. So the bearings were growing thermally in unusual ways, the bearing housings and the bearing itself. And they were also having a thermal stress, transient vibration inside the rotor of the IP turbine, mostly. As you can see, the bad actor here is mostly the IP turbine with the purple and the tan, and below that we have more reasonable numbers. For example, we have the HP turbine bearing. If I can get my mouse so I can find it again. There we go. You see the black line. The HP turbine is running something like at 60 maximum, 60 microns, which is nice and smooth. It's great. So we're mostly talking about the top three. Well, we have the HP turbine Y probe. I'm sorry. HP turbine Y probe is not healthy. That's the green one. Yeah. Okay. Okay. We're gonna get down to the machines now, closer. One more example of sources of the vibration. Here we have a 90 megawatt steam turbine rotor. It's a combined HP and IP, LP, looks like LP also. It's a single casing turbine, 90 megawatt combined cycle steam turbine. The turbine experienced high vibration relative to thermal loading and power load. So shaft power load and thermal load, both. The user found the evidence that there was a rub. Obviously, it must have been by vibration evidence. The rotor experienced shaft deformation due to packing rub. The rotor was sent to a specialist company, MDNA, and I put their their web address there just for information. The high pressure rotor was received and had a bow, a fixed bow in the shaft of 40 thousandths of an inch total indicator reading, which means 1 millimeter bend in the N3 packing gland area of the rotor. This amount of runout would not allow the rotor to spin up through critical speeds, so the machine just couldn't operate. You'd be rubbing everywhere. The rotor was successfully straightened, and what you see in the picture are thermal heating wires, in resistance wires, and they're insulated with the white insulation blankets that you can see. So they have to heat up the rotor, and then they will straighten out the bent part. Typically, they'll try to heat it first, and we're talking very good temperatures. I mean, they have to heat it to at least around 1,000 degrees Fahrenheit, preferably no more than that. So we have one more to admit. Okay. And that heat will allow the rotor to, instead of be kinked, it will now grow thermally in the axial direction freely, because it might be held there, as you see on the boring machine, but it's actually on one side, they'll allow it to slide. And the heat is going to allow it to grow freely, thoroughly, radially and axially, and for enough time. Then actually, once it's reached heat, I suspect they're probably going to rotate it so they can make sure that it doesn't get a bow due to the 1,000 degrees Fahrenheit, because to get rid of a thermal bow that's stuck in the rotor, they might have to start at 800, and they might need to go all the way up to 1,000, but that would be the limit to get rid of that fixed bow in the shaft. And then they'll probably rotate it as it cools so they get a straight shaft. Later on, if that doesn't do the job, they're going to have to also add heat and then use a hydraulic press with heat only, uniform heat on it, to straighten out the bad kink in the rotor. So they were able to successfully straighten it within 3 thousandths of an inch, total indicated reading, using a thermal straightening process. The HP rotor was then high-speed balanced and overspeed tested, and it was put back in service with no problem. So that's one example of where you can't solve this thermal-induced rub and thermal-induced trouble on this machine without removing the rotor. It's too late. Once it's got a permanent deformation, it's not going to be able to be fixed. It must be removed. Okay. So now we'll look at a case history in Kosovo, thermal power plant. It's a 339 megawatt thermal power plant, and the problem is in the generator and the exciter bearing next to it. So this generator, 339 megawatts, was field balanced in its bearings using the steam turbine to drive it, obviously. And the field balancing, you can see the results in the prior to balancing and after balancing. We have the bearing B6 and bearing B7 and bearing B8. B8 would be the bearing of the exciter. So B6 and B7 are the two bearings you see in blue color in front of you. And the vibration here is measured in millimeters per second. So I believe they were using the older technology of shaft reading seismic probes. I doubt it is the bearing housing vibration. It looks like it's a shaft reading, direct shaft reading, where they put a seismic accelerometer on a shaft rider, they call it, on a shaft rider, and that measures the shaft vibration directly. That was the old method of measuring large steam turbine generation units vibrate.
We still have it for some old steam turbine in Australia, and yes, they call it shaft riders. That's correct.
Okay. In Australia, you have it now. Okay.
Yes. Yep.
Thank you. Thank you. So you can see the drop in vibration after balancing. We went from, let's say, B7 went from 13.1 millimeters per second velocity, went down to 4.21. So roughly 1/3. The same for B8 from 15 millimeters per second, which is a lot, by the way. 15 millimeters per second. This is basically 12.5 millimeters per second is half an inch RMS, whereas 15, that's like 0.6 something, 0.65 inches maybe per second RMS. It's very, very high. It's a lot of energy. It's a destructive energy. So some people don't have an idea of what is the difference between rotor energy and acceptable rotor energy, unacceptable and acceptable. Unacceptable rotor energy is that which causes damage to the machine, whether it is in a short period, 1 or 2 hours, or whether it's measured in days and months. It should be that a rotor, as it vibrates, does not cause any destructive damage to the machine, meaning no babbitt impacting, no babbitt fatigue, the babbitt of the bearings, no fatiguing of the bearing housing supports, and no fatiguing of smaller bore piping connected to the turbine. All of these are ending up as damaging vibration. Whereas when you have a smoother vibration, which we call acceptable limits, the machine can run for years and it hasn't damaged the bearing or the supports or anything connected to it. Okay. So anyway, we end up here with 4.21 millimeter per second and 5.92. And the highest, which was the axle, was 19.51 millimeter per second. It dropped down to roughly 7 millimeters per second, which is kind of acceptable, yes. As a field balancing, it's acceptable. So when the machine was put back into service, unfortunately, it still had problems because they did what's called an unloaded balancing. The generator is, the steam turbine is driving the generator at the rated speed of 3,000 RPM. However, the rotor is not connected to the grid because they're doing what's called maintenance work on it. So they obviously have disconnected electrically completely and isolated it so they can add the weights and do the balancing safely. Okay. And so you can see where the balance plane is on the green part, which would probably be the fan holder, or the fan holder. Maybe it's the balance plane. And you can see they attach 750 gram on one side and 750 gram on the other, according to their balance program. Okay. So as we can see here, the vibration on bearing B6 is reaching the highest. On the axial, it reached 14.59 after startup. As you can see from the left to the right, we have the speed at 1,000 RPM, 1,500, 3,000 RPM, and then after 3,000 RPM, then loading with 100 megawatt. Remember, it's a 339 megawatt rated. So they loaded it with 100 megawatt and then took a reading. Then loaded with 152 megawatt and took a reading. And then loaded with 200 megawatt and then took a reading. And then 250 megawatt and then 250 with MVAR, higher MVAR. So if you recall in the previous slide where I had said, look, if you're going to balance the generators and rotors and steam turbine rotors and gas turbine rotors, you must operate them preferably at a no load condition first, and then get full readings at that point, and then go to a half load if you can, and then go to a full load. You want to have all this, the zero load, full, half load and full load. Don't jump from zero to full load. you're going to get insufficient data. You want all three. Okay. So we have also high vibration, we said, resulting on the B6 and B7 and B8 bearings. The highest we can see here on the axial, 13 millimeter per second. We have on the radial B7 vertical, 6 millimeters per second. This is not disastrous. Then we have.
I'm sorry, Mr.
I need to.
Could you please mute
Yeah, I will to find out. It didn't mute them.
Just Yasser, if you could please mute yourself. Mr. Yasser, if you could please mute yourself.
Can everybody mute, please? Can everybody mute? Thank you. Everybody just please mute.
Thank you.
Yeah, I know somebody's still not muted. If everybody can please mute your microphones.
Yes, Mr. Yasser, if you could please mute yourself.
Okay.
If you could please, Abdurrahman, you have this option, you can mute all.
Yeah, I did it, but it would not mute all. I applied it. I said mute all.
Yeah, I'm not sure.
Okay. Okay. Let's see what happens. Okay, finally. It has a lot of unusual commands now. Okay. So we have a vertical vibration. We have the B8 is still having a high vertical vibration of roughly 8.46 millimeter per second. And we have a vibration of 5.87. And this is after it was smoothly balanced, by the way. And how do we know it was smoothly balanced? We go back to the first. We reached 3,000 RPM and we only had, well, not so smoothly because it has some other problems, doesn't it? It's at 4.34 in the vertical direction and 5.17. And then we ended up with 8.46 after full thermal loading and loading from the power generation. However, why it's 4.34 and it was so smooth, for example, at 1500 RPM, 0.36, for it to go from 0.36 to 4.34 means there's a misalignment inside the machine. There has to be, especially when you see the high axial up here. So what did they find when they worked on the rotor? Next. They, because of this vibration, they expected there's something wrong with the generator itself. And they realized that we're going to have to solve it. So they took it apart and they found this generator rotor winding bars are elongated. So if you come up with this situation, either you do a temporary field balance until you can overhaul it, or you go in and you put in the spare rotor. Hopefully you have a spare generator rotor and you use that. If you don't have a spare generator rotor, then you have to fix it. But sometimes this can be balanced in place. It solves the problem temporarily. Not fully balanced, partially balanced. Okay. However, as we said, there's a heavy misalignment in this machine between the generator and the other driver, which would be like the LP turbine. The LP turbine is bolted to the generator. So there's definitely a misalignment occurring. Are there other issues involved? I don't know exactly on this case. It could be there's bearing issues they're not aware of. Could be there's other issues, because when we see failure analysis on vibration reports, sometimes the person has not captured all the causes. Okay, so if we come to thermal transients, vibrations caused by thermal transients, what are the root causes in generators? Shorted turns, blocked ventilation holes, unsymmetrical cooling, insulation variation, wedges fitting or tight slots, wedges not fitting well or tight slots, retaining ring, centering ring, assembly movement, heat-sensitive rotor forgings, distance block fitting incorrectly or not fitting well. So generator rotors are, which we see up here. Generator rotors have many mechanical components and electrical components. And there's many sources of where they can have thermal transients due to internal problems. And if you have to be careful of thermal transients in generators, because they can be, the generators can be actually trying to almost close to a more dangerous condition of a short circuit in the rotor itself, for example. So it has to be carefully analyzed, the generator, when it's going through heavy thermal vibration, thermal transient vibration. Next example, we have this, we only have 2 more slides and we're done, gentlemen. Next example, we have a thermal transient here, 3000 RPM turbo generator unit suffered from abnormal vibration fault of its generator. These are the 2 bearings of the generator, A, B, C, and D. A, B are one bearing, X and Y, and the C and D are the second bearing, X and Y. This is the vibration showing direct overall vibration and synchronous vibration in red color. And you're showing the amplitude with time. So the 3000 RPM generator suffered from abnormal vibration. Its first and second order critical speeds were 1052 RPM and 2736 RPM, respectively. Now, the 2736 might sound not good, but it's still 10% away from your 3000 RPM rated speed. So actually, there would be no there'd be no sensitivity to this, to the second critical vibration there, unless you're going through rundown as you go slow down again, or ramping up. Now the shaft vibration, so I'm just excluding that as a possibility that it has something to do with this fluctuation. It's too far from the rated speed. Now next, the shaft vibrations fluctuated periodically in constant speed operation. Obviously it's a generator, so the generator always runs at constant speed. Once you raise it to its rated speed, any load variation is not causing a speed variation. So the synchronous component in red color was dominant in frequency spectrum. It was roughly 90% of the total amplitude was the synchronous component, which is a good sign. It's healthy to a certain degree, okay? First of all, it means there's no subsynchronous vibration. If there was subsynchronous, we'd see it low, and there was no subsynchronous here. Fluctuation cycle was 24 minutes. Direct vibration amplitude at bearing A, okay, so the top would be bearing A, the top 2 are bearing A, fluctuated between 63 micrometers and 95 micrometers with a range of 32 micrometer delta. Okay. Now, when the machine was troubleshooted, they tried to first do a balance to see if that helps the situation. Because is this thermal related? Yes, it is thermal related. And it's in the generator. And so it's something in the rotor itself or interacting with the stator, because the stator is electrical also. So, they said, okay, let's balance it first. So when they balanced it, it actually dropped down from a maximum of 95 micron down to in the range of 40 micron. And the fluctuation went away. The fluctuation, this high fluctuation level of 32 micron went away. It became almost like 5 or 10 micron maximum, which is acceptable. 5 or 10 micron fluctuation is perfectly acceptable for an electrical machine. In fact, that's something we should discuss now. What's the acceptable fluctuation for an electrical machine? Let's say it's a 10 megawatt generator, 20 megawatt generation, 100 megawatt generator. In my experience, 10 microns is perfectly fine. Up to 12.5 microns, half a mil is perfectly fine, nothing at all, not worth any trouble. However, if you're going up to 1 mil fluctuation and above, which is 25 micron or more, there's something wrong. It should not be fluctuating with 1 mil vibration, unless there's other factors involved, which is like day to night misalignment. So if you can trend this with night and day and ambient temperature. So you'd add a trend to the same plot you see now here in front of you. You'd add a trend to it, which is night and day temperatures. to see if it's going up and down with night and day. And another trend you would add plot on the same plot would be cooling lube oil temperature. Sorry, lube oil temperatures going to these bearings. Then you would add other issues such as it could be steam exhaust pressure, for example, because it varies from night and day. So steam exhaust pressure and others. You can add other transient trends that give you more information here. Anyway, what they did when they added the balance weight was they achieved a smooth balance. And so they considered that it was a whirl that introduced this thermal induced vibration at the bearings themselves. This is their interpretation, not mine. So they considered that it was a thermal whirl, or it was a mechanical whirl caused by unbalance, but it introduced thermal effect at the bearings. And they considered the shaft would get hotter at certain parts of the shaft and inside those bearings. I don't have really a good idea and a good drawings of the whole machine and the bearing for me to judge that part of what they considered the cause. Although one issue is that if you have a rotor and it is bowing and it's showing this kind of vibration, let's say 90 micron, which is roughly 3.5 mils, 3.5 mils vibration. It conceivably, it could be that the shaft is due to this kind of bow in it from the, as you know, even unbalance, when it's high, it causes a fixed bow in the machine as it's running, because the unbalanced masses are forcing the body or the rotor to twist at a certain twist angle, because they're unequal forces, and you have this unbalance at different sides of the machine, so it's forcing it to twist. This actually causes a misalignment of the axis of the shaft to the bearing, a certain amount, and depending on where the bearing is at a node or not. So if what they're saying is that this, as the shaft was misaligned due to the unbalance, it's not causing an excellent contact pattern. It's not causing proper contact with the bearing, and therefore it will whirl inside the bearing due to this. And it might have a different temperature. This is conceivable, because the shaft might be touching more in one areas and not touching in other parts of the bearing, and then it would get hotter at that contact area, and it would be cooler at the non-contact areas. And that would, it kind of makes sense. So that if we balance this rotor perfectly or very well, instead of the 90 micron, it went down to, let's say, 30 micron, for example, at that point, the shaft is straighter in the bearing, and then there would be less thermal deflection. So I believe he means there's an intermarriage here of the unbalance with the thermal deflection at the bearing. It's unusual to me, and it's a nice case history. And final slide we have is an example of again, another gas turbine driven compression train, or sorry, gas turbine driven steam turbine generation unit, all on one shaft, And here I just captured this as a nice example where the author recommended to use, when you're judging the thermal transient vibration unbalance, plus you have the fixed unbalance of the rotor, the cold unbalance of the rotor, and you're trying to resolve both. He recommended, if you notice on the left-hand side, compressor end, this is the gas turbine compressor end bearing, balancing calculation based upon temperature data at 30,600 RPM. Balance plane 1, trial weight added was 20 ounces at 0 degrees, okay? And one more. And total balance needed, according to the balance calculator, needed 40. So with a trial weight of 20 ounces, when they tried this method, they found that it's not doing the job well enough. So then the balance program is saying, make a total balance weight of 40 ounces at this location. And then a trim balance of 21 ounces to the left on the pinks one. However, it's because they used data which are not at steady state. They were more at a 3,600 RPM, but not capturing the different loads at different speeds. So if they had operated either with various loads, like a 0 load, 25% load, 50% load and 100% load at 3,600 RPM, and then made calculations based upon each load, and hopefully try to average. If they notice that the machine is reversible as you went to 100% load, then you brought it back down to 25%, and you found it was reversible, then it means you're going to be stuck with this variation always. If you solved external problems, going back to our initial discussion, the third slide, is first solve other issues, nonlinearities in the machine bearings and others. But coming back to that, say you have solved them, then the author here says, okay, use various balancing speeds to get a better accurate idea of the phase angle of the unbalance here. So don't only use the 3,600 RPM. Here it's a variable speed machine because it's gas turbine driven. So this must be a cold balancing, because they're balancing at the compressor end. They don't have to balance the generator with electric power going through it. If they're going to balance the generator, they're going to have to run it at 3,600 RPM only, and then vary the load, and then get that. But in this case, they're not trying to balance the generator. So it means the generator can be isolated from the electrical grid completely and just run cold, because there's no problem with the generator. The problem here was on the compressor end bearing. So they're trying to balance it there. And to balance it well, he says, okay, balance it at various speeds. Like for example, 3,000 RPM, 3,200, 3,400, or achieve, take readings at 3,000, 2,800, 3,400, 3,600, and find out what are the unbalanced vectors at each of them, and follow the phase angle where it's going. So you're going to be plotting it on different plots from the actual data as it comes out of your Audrey or whatever. Better to just take them and plot them on paper. Say, okay, at 3,200 it was this. And then you'll know exactly where is the real phase angle, where's the correct phase angle, and what is the real unbalanced vector, how much unbalance there is. So it's a way of maximizing accuracy of the balance calculation. So I just throw this as a last slide to show that the thermal transients come in and play with your balancing. So you have to know how to deal with them. Thank you very much, gentlemen. And I don't know, Salah, did you normally give time for questions or? Hello, Salah.
Yes, yeah, I can talk now. It's depend on you, because this is the last session for today. So if you have time for few questions, we can go through them. Like I have a few questions on the chat, because we'll not be able to go through all of them, but I can read a couple of quick questions. First, I got very good feedback, and everyone saying it's excellent presentation, and really it is. I enjoy it. You are very talented and skilled, was very high experience person. That's something we all know. I just got here a couple of questions. What is the main cause of the sub-synchronous frequency at 0.4x for turbine with tilt bad bearing? Only at no load full speed condition.
Okay, so
it's very generic question, you know. Like,
yeah, it's also come out of our discussion subject. We were discussing thermal and
yeah,
but we'll take it. Okay, we'll look at it. Can you repeat the question again?
What is the main cause of the sub-frequency at 0.4x for a turbine with tilt bad bearings, only at no load full speed condition, with about 80 micron, like the vibration level at 0.4x at no load condition about 80 micron?
It could be multiple issues. Number one, something could be exciting the first critical. If the 0.4x is the actual first critical speed of the machine, something exciting it, like it could be a light rub that is exciting the 0.4x. So he should, number one, search for a light rub and confirm that the 0.4x is actually his first critical speed of the rotor. Okay, that's number.
The rest of the question, sorry, Engineer Abdurrahman, he's saying, and with the load increase, this reached to 5 micron, like the vibration about 80 micron at 0.4x at no load, and when the machine is loaded, it's dropped to 5 micron. Like one of the things came into my mind as well. Uh, when you have this much drop in vibration level, when the machine is loaded, it could be whirling. Because when you have no load on the shaft, you will have a very low eccentricity ratio, and then the upper hand will be for the oil. So the oil can control the shaft movement and cause high vibration. And when the machine is loaded, you increase the eccentricity ratio, so you became far from the threshold of the whirling, and then you have low 0.4x, for example. Because I had yeah, similar
Okay.
condition. Yep.
Yeah. Okay, I'm just calculating in my head. One thing, this could happen, what he just mentioned, in your explanation could be when it's a high-speed turbine. But in my head, I was still stuck in power generation, 3,000 RPM.
Yep.
So if it's a high-speed turbine, whether it's driving a generator through a gearbox or whether it's driving a compressor or other drive, and if it's a high-speed turbine that might be at 7,000 RPM normal, for example, or 8,000, then it's, it has a tilting pad bearing, you said, right? Tilting pad?
Yep.
It's happened rarely, but in that case, it was only when the tilting pad bearing had excessive clearance.
Yes.
So, and we know one thing is most manufacturers don't have any bearing specialists, and they don't understand how to select the bearing clearance.
Yep. Correct.
On tilting pad bearings. So I've noticed it, it's amazing. Many worldwide manufacturers are not aware of the exact bearing design. They understand rotodynamics very well, but bearing design is usually a specialist consultant who's highly specialized in bearings alone, and he knows these secrets, but the manufacturers do not. So you'll get a turbine, let's say it's 7,000 RPM, and it has let's say the shaft diameter at the bearing is 5 inches, or I don't know if you want to talk in millimeters, that would be 125 millimeters, for example.
Yep.
And the bearing clearance, the diametral, we call it diametral, so we're not talking radial clearances, we're talking diametral clearance, meaning total clearance between the shaft and the bearing. It should be on a steam turbine roughly 1.25 or 1.2 times diameter over 1,000.
Yes, that's correct. Yep.
The cold clearance. Now, if you're at the hot end, you add a few thousandths of an inch to counter for thermal growth, depending on the size of the machine. But I don't know, it sounds like he doesn't have a very large machine. Since he ended up with the world, it must be a lightweight rotor. That means it's running at high speed. So a lightweight rotor at high speed, bearings are definitely not more than 5 inches diameter. His shaft is not more than 5 inches diameter. So we're talking roughly about, on the hot end, he's going to see roughly 3,000ths of an inch thermal growth, maybe 4 maximum, 3 to 4. So it means he should be 1.20 times shaft diameter of 125 millimeter over 1,000 times, plus 0.003 inches clearance to make up for the thermal growth, or 4. Could be 4. It depends on his shaft diameter. Might be 4 at the hot end of the machine. At the cold end, it's going to be much closer to normal. It's just 1.2 times shaft diameter over 1,000 plus 1,000 to counter for the thermal growth. So he's definitely, it's very possible he has an oil whirl caused by very excessive clearances in a tilting pad bearing. In a normal designed, well-designed clearance thermal tilting pad bearing, there's no such thing as oil whirl anymore. It's completely eliminated. It cannot whirl. However, you can have a steam whirl in such a machine. You can have in a steam turbine with well-designed tilting pad bearing, you could still have a steam whirl, but in his case, he said it only happened at no load. Therefore, with load, there would be steam, but he says it happened at no load. It means it's not caused by steam whirl at all. It's not steam related. As if his facts are correct, and it only happening at no load, most of vibration, then it's closer to what you said, that it's some kind of oil whirl. And I also add another one here is, these machines, they have vibration sources living inside them. As you can see here from the slide, we said that these steam turbines used to drive the users crazy sometimes, because they have vibrations that they didn't understand why they're vibrating. Now, the reason why a machine vibrates is it's the damping of the bearing is insufficient to react and dampen the rotor vibrations. So we have somebody who's trying to enter. Okay. So if he's using like an ISO VG32 oil in this bearing, he's going to have damping. He's going to have poor damping of the shaft. He should go to the next size up oil, which is ISO VG46. has more damping, and people don't realize why. They think that ISO VG32 is lighter oil, therefore it's great for, it's a high efficiency, means it's not having much shearing, and we have lower thermal losses in the bearings. And it's still doing the lubrication job. Yes, it's doing the lubrication job, but you're walking close to the edge of a cliff. The ISO VG32 oil at the bearing average temperature in the bearing loaded film area, let's assume it's 160 degrees Fahrenheit average temperature at the bearing loaded at the highest eccentricity ratio, which is the closest the shaft gets to the bearing. The average might be 160. Now, the ISO VG46 oil at that same temperature, 160, shearing at that same location, has basically 50% more viscosity, and therefore 50% thicker oil film. So it separates the shaft from the bearing by 50% more, greater oil film thickness, the minimum oil film thickness. The second thing is there's a oil arc, an oil pressure arc that is causing hydrodynamic effect of lifting the shaft. This arc is much larger when it comes to the ISO VG46 oil. So it acts as a hydraulic damper, a large one, whereas the ISO VG32 acts as a small hydraulic damper. It's a small arc only because it had to be at the edge where the shaft rotates and the oil has escaped. Now the oil is leaking out and the pressure goes to zero. Theoretically, it goes to zero, even though it's under the shaft. It reaches zero. But if there's a thicker oil, this arc is much larger. Instead of an arc of, let's say, I don't know, let's say 30 degree or 40 degree arc, the arc can be 60 or 65 or 70 degrees of pressurized arc due to ISO VG46 oil. So you have much larger damping and insignificant extra friction resulting from the ISO VG46. It's not significant, not even worth discussing, the increase. So these are the factors. He needs more damping. He needs to fix this. That's what it looks like, but without getting more information from the author or the user, we cannot judge this more.
Yep. Just one more last question, because there will be lots of questions. Just one last question. In a brief, if you could please, how you can distinguish between the thermal unbalance and the magnetic unbalance on generator rotor?
Yeah, this is a really nice question. Excellent question. Was going to get more into generators, but the problem is the slide would become, the presentation would become longer. So the magnetic. We had another generator drawing here. No, okay, we'll just use this generator drawing. Now, the magnetic unbalance will be load related, but it is going to be much shorter time, the time transient, thermal transient. If it's thermal heating on this rotor or thermal heating in the stator, for example, if there's a problem in the stator, it can also cause trouble, by the way, for the rotor. It causes unusual vibration there. I'll show you why. For example, if you have a stator here and you have a high temperature right there due to insulation problem right there, it will heat the rotor where? Notice it's not touching the rotor, correct? But it will induce from radiation and convection to induce heating of the rotor right there, even though there's no contact, and therefore it will heat it up here. And what happens? It's going to start to have a thermal bow, even though this is rotating and it's going to be almost equal temperature, but it's going to be unequal in the axial direction. Like here it might be, who knows, 100 degrees Celsius or less, and here it might be 150 Celsius.
مش فاهم عامله هنا عايز يحط مع
Okay, I need to mute all.
Mahmoud Alem, if you could please mute yourself.
Okay. Yeah, I muted them. Yeah. Okay. Okay, I got them muted. Okay. So the magnetic forces are going to be different than a thermal vector, thermal unbalance inside the rotor or inside the stator, because they will typically caused by non-centering of the rotor in the stator. So as it is non-centered in the rotor is non-centered in the stator, it not only develops a 1x, but it also develops a 2 times vibration frequency. And you're going to get a 2 times vibration effect when there's a magnetic unbalanced force, and not only a 1x. You're going to get it 2 times also. Exact magnitude of the 2 times will depend on the load, for one, and it will depend on the bearing damping ability and other factors. But there'll be much more 2x vibration that will be electrical. And you can judge it on a rundown, on a Bode plot, by shutting off the electric power. And as you're measuring the vibration, you'll see a very sharp change in the 2x. The 2x goes away very fast, which shows you it's electrical. It's not mechanical 2x. And the 1x will drop suddenly. The magnetic 1x will drop suddenly. Whereas if it's a thermal, it doesn't, the 1x will not drop suddenly because you're running at full thermal and then you suddenly shut off, but it stays there because that heated part stays hot. And it will stay gradually during the Bode plot. It will be more gradual rundown. Whereas when it's magnetic, no, the magnetic power is gone immediately as soon as you shut down the generator or motor. And so you will not see the 2x anymore, or most of it's gone. And the 1x caused by that magnetic power will go suddenly, but the remaining residual unbalanced 1x will still be there. I hope we answered it properly. Thank you. Salah, are you on?